Hi, everyone. Thank you for joining Riot's Lunch and Learn series today. My name is Caroline Griffin. I am Riot's Director of Operations, and I'm super excited to have Clint Olsen with Cardinal Peak here today to give us a technical overview of LoRa and LoRaWAN. Just a couple of quick reminders before we get started. Please keep yourself on mute. If you do have any questions throughout the presentation, I encourage you to use the chat box. Clint will be pausing periodically throughout the event just to answer a couple of those questions. If we do have a large overflow, we'll answer the remainder of the questions at the end of the presentation. This presentation will be recorded and posted to Riot's YouTube channel and then posted to the meetup group and where you registered for this event, so you'll be able to catch it later. But without further ado, I know you are all here to see Clint, so I'll hand it over to him. Thanks for joining us.
Great, thanks Caroline, and thanks for the introduction. And I'm really excited to be here. This is my first presentation with Riot, my first experience with the group, so I'm excited to be here. And I really want to thank everyone who's taken time out of their day to come watch my presentation today, and I hope that you find it to be informative and useful. So as Caroline mentioned, today's talk is going to just be a technical overview of LoRa and LoRaWAN. And just to give a couple of quick intros, my name's Clint Olsen. I'm based out of Colorado, and I'm an embedded software engineer for Cardinal Peak. So just a quick plug for Cardinal Peak. We're an engineering services company also based out of Colorado, and we've been around since 2002. And we kind of work in a lot of different areas that relate well to the IoT space, which will relate back to the talk today with LoRa. So we do work in embedded cloud, quality assurance, UI, and a little bit of hardware as well. So we work with our customers on a variety of different areas within your product development. And we do this in a variety of markets as well. So a lot of consumer work, audio, video, healthcare, and automotive. So if you have any questions about Cardinal Peak, you can reach out to me. And I just put a link to our About page here as well. So just to give a little bit of background about the content of the presentation today. So last year, I got the opportunity to work on an internal project at Cardinal Peak, where basically my goal was to, learn about LoRa and LoRaWAN and kind of create some learning tools and some documentation for engineers internally to be able to, help jumpstart some development if the need came up, or if someone was interested in learning more about the technology. So I hadn't heard of it prior to starting working on it, so I got to do research and learn about it and create some content, and as well as set up a LoRaWAN network at our office to use as basically a learning platform for our engineers. And so I definitely won't claim to be an expert in the topic, but I'm gonna just share with you what I learned and just some of the basic topics, and I'll provide some resources as well, and we'll answer any questions, and if I can't, we'll try to direct you to just some documentation or some resources that can help you find the information you're interested in to either try to jumpstart some development in your respective companies, or if you just have a personal interest in the topic as well, it's an easy thing to delve into and start learning about. So let's start talking about what these technologies are. So LoRa is a wireless protocol that's really meant to be used within the IoT space. And if we look at kind of the spectrum of wireless protocols in IoT in general, there's kind of different categories that we have based on a few different factors. So LoRa itself falls into what's called LPWAN. So this falls into a category that tries to maximize range and low power. And so with the diagram here, you can see a few different areas that you may be familiar with, such as PAN, Personal Area Network, or LAN. So essentially what this plot is showing that you get to pick two out of the three that you get, with the three being speed, power, and distance. So with a technology like Bluetooth, you're really striving for speed and low power, but really the sacrifice you make there is distance. And so the void in the spectrum that LoRa tries to fit into is obtaining low power with a long range of communication. And the trade-off there is that we get a lower data throughput. So this is really ideal for sending small amounts of data very infrequently. And what does low data throughput look like? That's anywhere from hundreds of bits per second to 10 to 20 kilobits per second. And so another question might be, what defines low power? And this is really an implementation specific factor that depends on, how the radios are configured and largely, kind of the environment you're working in. But the goal of the technology is to be able to operate a low power embedded device for months at a time, or even longer off of a single coin cell battery is kind of the base example that they use. So, and if I didn't specify, so LPWAN is the category that this falls into, and that's low power wide area network. And there's other technologies as well that fit into this that try to accomplish, the same goal, just a slightly different way. But in this talk, we're going to focus on LoRa, which the name LoRa is really just a abbreviation for long range. So the title of the talk today is LoRa and LoRaWAN, and I just want to take a moment to kind of specify the differences between these two things. So LoRa is actually an RF modulation technique that's implemented in the physical layer of the respective radio for the device. And so this is a proprietary technology that's owned by Semtech. And so not all of the details are readily available, but a lot of the content we're going to talk about today is from higher level documentation, and as well as some reverse engineering efforts and looking at some RF captures of transmissions being sent and things like that. So LoRa operates in the ISM band, and this is regionally specific depending on country mostly. So in the US, the base frequency is 915 megahertz, and the diagram on the right kind of shows at the physical layer at the bottom, the operating frequencies in different regions, so Asia and Europe as well. So to distinguish between LoRa, so LoRaWAN is actually a software specification that is defined by the LoRa Alliance. And so this is really a software stack that sits on top of the LoRa PHY. So you can kind of think of this as similar to the Bluetooth specification defined by the Bluetooth Special Interest Group. So this is defined by the LoRa Alliance and is open source. So you can just get the specification without having to pay or anything like that. So this really defines the packet structure, how security works in the network between the different devices, how devices are configured, as well as the different devices within a LoRaWAN network. So it defines the topology. So I put a link down there at the bottom to the specification. So at the time I created this, I think we're at V11, or it might be 1.1 was the specification for LoRaWAN. So I'm sure that they've updated it since then. So you can go through and find all of the documentation that defines the different features that may have been added since the creation of this presentation. So we've talked about this, this area of operation that LoRa is really optimized to be used in. And so the question might be, what applications actually would need this, longer range of operation with low power, but having the sacrifice of small amounts of data. So there's a lot of metering technologies out there, or applications, I should say, that cater themselves well to this. So something like smart agriculture, where we're monitoring, animal well-being or irrigation, things like that, to measure water flow, where we can, very infrequently obtain the data and get, a useful application out of that data over a long period of time. And so kind of an interesting specific example that I read about was a Korean company that created an ingestible pellet for cattle, and it operated with a LoRa radio inside of it and a small battery, and it was created to be used for around 7 years. And the cattle would ingest the pellet, and it would embed itself in the lining of the stomach, but once a day would ping back biometrics about the cow to a hub, so that the cattle farmers could monitor the health of their herd. And so that's kind of an interesting application. And as talked about before, utility monitoring and various other small data consuming applications lend themselves well to this. So I put a link there to the Semtech website that has a lot of detailed case studies and examples of what might be a relevant application for this technology. Okay, so that's basically the introduction to the topic. So Caroline, do we have any questions at this point?
No questions at this time, Clint. Thank you.
Okay, great. So from here, we're just going to jump into the technology. So I've broken this up into a couple of different segments. So first, we're going to talk about LoRa, so the actual modulation scheme itself. And so as I mentioned before, this is proprietary. So a lot of the information here has been derived from higher level documentation that's available, as well as some people, analyzing the transmissions and trying to understand what's going on. So the real details are classified, but based on these efforts, there's a pretty good idea of how this technology works in general. Okay, so the LoRa modulation is basically a mixture of a couple of different fundamental techniques in RF. So the LoRa modulation is a combination of chirp spread spectrum and frequency shift keying. So with frequency shift keying, that's essentially encoding data in changes in frequency. And so the figure on the left there just shows like a basic FSK modulation where we have a high frequency representing a 1 and a low frequency representing a 0. And then what LoRa does is it uses this notion of a chirp, which a chirp is shown on the right, the far right there, which is essentially a linear sweep in frequency over a period of time. And so the center image there shows this in the time domain. So basically an increasing frequency over a specific period. And so the frequency shift keying comes into play when we try to actually modulate data or encode data in these chirps. So there's a notion of up chirps and down chirps, and essentially where we begin this frequency sweep within the period of a particular chirp will determine what data value is encoded in that particular chirp. So this is just kind of a close-up view of an up chirp. So it just shows the sweep of the frequency across what's called the bandwidth. So that's basically the frequency it covers over its sweep over a given period of time. So we'll discuss the bandwidth because it actually has a little bit more significant meaning as well in the configuration and in the definition of the modulation. A couple of important terms to understand, and these really translate to configurable options within the radio itself. So one of the most important is the spreading factor. And so what the spreading factor determines is the number of bits per symbol, which in this case, a symbol is one chirp, and it determines the slope of this chirp. So essentially, how quickly are we sweeping across the bandwidth? And the figure on the right there shows a configuration at different spreading factors. So the far left is an SF7 configuration where you can see we very quickly sweep across the bandwidth. Whereas on the far right, there's an SF12 configuration where it takes much longer to spread across this frequency, or to sweep across the bandwidth, I should say. So the bandwidth itself is, as I said, the frequency width of the chirp, but this also defines what's called the chip rate. And so there's this notion of chips and chirps, which can kind of get confusing because the words look similar. But a chip is essentially a even subdivision of a chirp. And so basically a chirp is consisted of a number of chips. And the next page I'll show kind of mathematically what these chips represent and how you can kind of relate them to data that's encoded as well. The data rate is the number of raw bits that are sent per second. And I'll make a distinction between data rate and the raw data rate, and as well as the regular data rate on the next page, because there's a slight difference there. And then the final one is the symbol rate. So as I said before, the symbol in this case is a chirp. And so this is the frequency over which we're experiencing a chirp in time. So on the left there's a diagram that kind of shows the different trade-offs that you get with some of these configurations, specifically with the spreading factor in this case. So the SF12 configuration really is trying to maximize range. because we're really spreading out the energy over a longer period of time. And so the total energy it takes to perform an SF12 chirp is higher, but we get a higher range out of it. And with the other side effect being this is the lowest data rate that we can obtain. So as we start decreasing the spreading factor, we increase the bit rate and the per chirp energy goes down as well. And so this is kind of one of the factors that you have to play with to be able to kind of cater the radio configuration to your particular application. So here's just a couple of equations to help kind of quantify what these terms mean in terms of the radio. So the spreading factor itself, the important thing to know is this is how many bits are encoded per chirp. And so looking over to the right there, relating chip spec to chirps, the number of chips per chirp is 2 to the spreading factor. So you can kind of think of this as like the numerical range within, like an 8-bit integer. This is kind of defining the same thing as where this is the range of values that you can encode in one particular chirp. So there's equations there for the chirp period and the chirp rate, which those are dependent on the bandwidth. So how much frequency do we have to cover within the period based on the spreading factor? And so using those equations, you can calculate your raw bit rate and your data rate. And so the difference between these is the data rate is the actual data rate for meaningful data, not including overhead. So the data rate includes the CR, which is a coding rate factor for something like a Hamming code that's tacked on to the end for data integrity purposes. And then from there, one of the other values to recognize is how bandwidth relates to chips. So essentially the bandwidth is also the chip rate. So this will determine, over our frequency sweep, how many chips will be, or the rate that the chips are put out that are transmitted from the radio. So trying to take these different values and these different terms and relate them to how it translates to data rates within the radio itself. The chart down there shows different configurations of bandwidth and as well as the spreading factor. So the configurable bandwidths are also a regionally specific characteristic. So for the US, there's an allowable bandwidth configuration of 125 kilohertz, 500 kilohertz, and I believe 250 kilohertz. So this kind of shows how these different configurations affect the data rate. So if we look at the two SF10 configurations, we can see that that's in SF10 at 125 kilohertz that we get a data rate of 980 bits per second. But if we look further down at data rate 10, that we have a spreading factor of 10 at 500 kilohertz bandwidth, and that bumps us up to 3.9 kilobits per second. So these are different configurable items within the radio that you can use to kind of cater the range versus data rate options that you need for your application. So now I want to talk a little bit about the modulation itself. How are we encoding data within these mysterious chirps that we've been talking about? So the unmodulated signal there is really just an up chirp without any breaks in frequency. And so what this really means is a transmission of all zeros. So a demodulated up chirp equates to a 0. So on the right there, you can see a modulated signal. And at the beginning of each chirp period, there's a chirp that's beginning at different frequencies. And so this discontinuity in the chirp is what is actually encoding the data itself over the chirp period. So kind of relating some of the equations that we were talking about before to this bottom example, they have a SF7 configuration, where in that case, that equates to 128 chips. So that's really the range of values that we can encode in a particular chirp. So think of this as like a 7-bit number, essentially. So the starting frequency of the chirp is what determines the value that's encoded. So that diagram down there shows the first chirp period is just a pure up chirp. So that results in a value of 0. The next one starts at the center frequency, which, since we're at SF7, we can have 128 values. That would mean the center frequency equates to 64, which is half of 128, and then just continues on and shows the different encoded values based on the starting frequency of the chirp. So this is a spectrogram of an actual capture of a LoRa packet coming across or being received at a receiver. And you can see there's, the series of up chirps and a couple of down chirps, and then some modulated data as well. So based on this analysis, the person that captured this kind of believes that this is the structure of the packet itself, where there's this preamble and then a synchronization with some down chirps to be able to indicate the beginning of the payload data. And so you can see the header payload CRC section is where we start seeing some modulated data that have these chirps beginning at different frequencies. That's, as we saw in the previous slide, what determines the value that that particular chirp contains. So just really quick to talk about the demodulation piece. So this is what happens on the receiver end. The receiver has to, capture this energy and be able to demodulate the signal to be able to get some meaningful data out of it. And so the diagram in the bottom left there shows the demodulation scheme, which essentially consists of taking a modulated signal that's received and multiplying it by what's called the inverse chirp. And so what the inverse chirp is essentially the complex conjugate of just a standard up chirp. And so I don't have the math written here, but really what this represents is a modulated signal for the chirp is a complex exponential with a time varying frequency component in the exponent. And so when you multiply by the complex conjugate of the standard up chirp, it essentially gets rid of that time varying frequency component and leaves you with a signal at a constant frequency. And so that's what the modulation diagram down there shows, is when you multiply by the inverse chirp, you get these decoded symbols, which really are signals at a constant frequency, where that constant frequency represents the value that was encoded in the signal, which is pretty cool. So that really tells you, okay, where did that frequency jump from the beginning of the period start at? And then you can relate that back to a physical number or of encoded data. So kind of the why of this modulation scheme is, when it comes down to it, is noise integrity. And that's what really allows us to pull the maximum range out of this technology, which is, what makes it powerful, is to be able to get low power with long range. And so on the receiver end, this modulation scheme allows you to actually receive at a negative signal to noise ratio. So the reason this is possible is because in comparison to something like frequency shift keying, where a lot of the energy is in the amplitude at a particular frequency, the energy in the frequency domain is spread out across more frequencies. So we're getting the same amount of energy, but at a lower amplitude. So the receivers are still able to pick this up even below the thermal noise floor. And so kind of a cool example of this, I'm going to pull up a link here demonstrating the range, is there's this LoRaWAN distance record. And so essentially the background behind this is a group in Europe decided to put some LoRa radios, so the low power embedded devices, up in essentially weather balloons, and try to see what type of range they could get out of it with an unobstructed view. And so that's really key, because practically speaking, getting an unobstructed view, like on the ground, is really difficult. And so they were able to get a range of 476 miles using 25 milliwatts of power, which is pretty cool. And this article just kind of goes through and shows how they did that. Can everyone see my screen? Sorry, I just realized I don't know if it's sharing the tab I'm looking at in my browser.
We can see it.
Clint.
Okay,
Yes,
great. So this kind of just goes through and talks about how they ran their experiment and shows where they had different receiver devices set up throughout Europe. And basically this is how they determined the longest range that they could get. So this is, all a testament to how the modulation scheme is designed to be able to work with this, have really high noise integrity, essentially. So, okay, so that's the end of the LoRa modulation part. Does anyone have any questions regarding that?
There's one question here. What have you found to be best practices related to setting the spreading factor for different types of data being transmitted?
For different types of data. So let's just go back so we can analyze this. So in terms of the spreading factor, just to give a bit of a recap on that, the spreading factor is really a trade-off between your data rate and your range. And so setting the spreading factor is really dependent on your application. Really, you have to start with what range are you hoping to get out of it, and as well as how much data you're wanting to send. And so really it has to be a balance of those two things. And so, for example, if you want to send things really fast, you're going to have to set it to a high spreading factor, but your range is going to be sacrificed by then. So the type of data itself, has to be something that is still useful at a lower frequency of reception, I would say. So I'm not sure if that answers the question specifically, but if not, please go ahead and clarify in the chat.
He said that was helpful. Thanks, Clint.
Oh, great. All right, so the next segment is talking about LoRaWAN. And so this is the software specification that's defined by the LoRa Alliance that sits on top of this physical layer that we've kind of gone through and talked about a bit. And so there's different chip manufacturers that actually develop LoRaWAN stacks themselves to provide with their development environments. So with their development boards and different chips and things. So I'll talk through some examples later, but ST is one example. They have a LoRaWAN stack that you can get from them and put onto some of their development boards to begin, jump starting some development and playing with the technology. So the first thing to understand about LoRaWAN is how the network is set up in this case. So we've really just talked about the very low layer. So now this is kind of taking that low layer modulation and how do we turn that into a useful application? What devices do we need based on the LoRaWAN spec do we need to turn this into a useful application? So there's several different devices in a LoRaWAN network topology, where starting on kind of the lowest layer, there's nodes. And so there's a few different names for these. They're called nodes or motes or end nodes. You'll see different nomenclature for these. But these are the low power embedded devices that are transmitting data that they collect to be used by the application. And so these will have a LoRa radio on them. And these transmit data to what are called gateways. And so the gateways are what receive this data from the nodes, demodulate the signal like we talked about, and they have to have some sort of backhaul network connected to them. So this could be cellular, Ethernet, or Wi-Fi to be able to send this data back to the server side of things. So there's several different servers that are defined by the topology. There's network servers, which these are really designed to identify devices that are sending data, make sure that they're part of the network, and forward these up to the application as well. They also perform some security functions and collect data about the device transmission and various things. And so above that, we have the application server. And so the application server is really the user-facing interface that's utilizing and consuming this data from the nodes. And so this is responsible for providing some sort of meaningful, useful application for the data. And then the other server is what's called the join server, and this is really designed to negotiate adding devices to the network, creating keys for security, and essentially managing those types of things. So we'll talk about each of these in a bit more detail. So the end devices are these dispersed low power devices that are meant to be operating for months and months at a time off of a single battery without having to be charged or anything. And they're able to uplink data to the network as well as accept downlinks. So the network server is able to send data if required. And so there's 3 different classes of transmission that are defined by the LoRaWAN spec, where class A means that data can be uplinked from a node at any time, but then downlinks can only occur after an uplink. And this is kind of the canonical class for these, where all devices must support this. So the other class is class B, is you can uplink at any time, but then you only can get periodic downlinks. And then class C, which when I was playing with some of the ST tools, actually, I don't think that this was yet supported. So there can be kind of a discrepancy between the tools you see and what the actual specification is, depending on the version. So, but anyway, this class allows you to uplink and downlink at any time. And what these classes are trying to do is kind of force a particular type of operation to maximize the low power characteristics of the radio. And class C is kind of dubious in this case, because it kind of allows you to send data whenever you want, which slightly defeats the purpose, because that ends up consuming more power, but it is an option. And one of the really nice aspects of this setup is that keeps things very simplistic, at least on the device side or on the node side, is that there's no really knowledge or information sharing that needs to be set up prior with a gateway. So as I said before, the nodes are sending all of their data to gateways. And so essentially they are sending encrypted data out, and any gateway that has a LoRa radio receiver on it can pick up this data. And so at that point, it's up to the higher levels to kind of make sure that this data is theirs and is part of the network and decrypt the data. But it keeps the development simple at the low levels. And the final piece of information here about the end devices is that they are actually the devices that initiate a join request to the network. So this ends up being a negotiation between the device itself and the join server. So talking a bit about gateways, as mentioned before, these are kind of the connection between the low power embedded device and the network itself for the application side. So this can be any type of backhaul network that connects to the server. And the gateway is responsible for demodulating the transmission and forwarding packets to the network server. And another important characteristic is that it collects metadata regarding the transmission. So this is things like RSSI, signal to noise rate ratio, and the data rate. And these different parameters can be used to actually dynamically configure some parameters automatically regarding the radio. If the data rate's suffering or the signal integrity is suffering, you can kind of adaptively change those things with something that's called adaptive data rate. And I don't really go into detail there, but this kind of allows you to change those things dynamically based on the physical characteristics of the transmission. So now moving up to the server side, the network server is what actually decrypts part of the packet sent by the radio to identify the device on the network. So at this point, your payload is still encrypted because there's different keys at each server level that are used to decrypt packets, different parts of the packet. And so the network server is what's able to identify a device that's on its network. And this is kind of the piece that, if it didn't make sense to you, why, oh, well, if any gateway can pick up my transmissions, how is that secure? Well, this is kind of the layer that allows that, because if it gets a packet that it can't decrypt, and then it just throws it out. And same with someone trying to inject packets and various things like that. It'll only recognize devices that it's been configured to understand. And so this performs a couple of other functions: deduplication of packets if they're resent or anything, and then issuing MAC commands. So this is media access control commands, which are really configuration for the radio itself. So this is how you can set things like the spreading factor and the data rate, kind of like what we talked about with the adaptive data rate. You can send different data rate configurations down to the node device. And that's what's really defined as the downlink, is when we want to send information from this level down to the embedded device. And how that happens is determined by the classes we discussed for the class A, B, and C for the node devices. So it encrypts the MAC packets, and it also just has a frame counter, like a nonce for like replay attack protection and things like that keep track of the frames coming in. So The application server is, as I said before, this is the user-facing application, and really one of its main purposes is to receive the payloads from the device and decrypt them and use them in a meaningful way. And so the network server doesn't have access to decrypt this part of the packet. And so the application server is what does that. And then the join server is what holds the root keys, which in this case is what's called the app key, which an app key is basically a predetermined value that's device specific. And I'll talk about that in a bit more detail in the next slide. The join server also creates the session keys, which, like I talked about, the network server and application server being able to decrypt different parts of the packet. That's because they hold different session keys. There's an application session key as well as a network session key that's used to decrypt this information. And the join server is what creates those and sends them throughout the network. Finally, since it's called the join server, it also negotiates join requests with the end devices, which this is based on configured IDs that they can agree upon between the embedded device and the server side to be able to recognize that, yes, I should be able to accept this join request from this particular ID because I'm expecting it. So there's two different ways to join the network in this case, and the diagram down there kind of shows the network layout again and shows how the keys are distributed. So I'll talk more about the keys when we talk about this over-the-air activation. So OTAA is kind of the recommended way of joining the LoRaWAN network. So having a node device join the network. And basically this is an over-the-network negotiated join request between the end device and the join server. So in this configuration, the join server will actually generate the session keys, which have to be distributed to the network and application server, but then also to the device itself. So this is how it encrypts the packet so that the network server can identify the device and how the application server can decrypt the payload and understand it. So the power with this is that these session keys can be refreshed every now and then. And so since they're not hard coded, they can be refreshed, which adds to the security of the network as a whole, so that if something odd starts happening, then they can refresh the keys and kind of ensure security at that level. So the other way that you can do this, which is kind of a easier way to get things jump started in development, is called activation by personalization, ABP. And this is where you actually hard code the session keys into the end device. And so kind of the fallback to that in something in more of a production environment is where you can't reflash the device or have a mechanism to update the keys, is you can't change them. So that kind of harms the security and kind of adds an inefficiency into a more like production type environment. So talking a little bit about the keys down in that OTAA diagram, the join server and the device have this device specific app key, which is kind of the root key for the particular device. And this has to be hard coded into the device at like manufacture time so that the join server knows how to recognize it. And so one of the advantages of this is it's device specific. So if something goes awry with that particular device, then it can be blacklisted from the network, and it only affects that one device. So you can't do anything to the other devices with that particular app key. And so the other keys are the network, the session keys. So there's the network session key and the application session key, which, like I talked about before, can be refreshed with OTAA and are used to decrypt the packets in a different way for device identification and payload decryption for the user-facing side. Okay, this final section is pretty short, so does anyone have any questions on the LoRaWAN section?
There are a few questions, Clint, but we do have some just general conversation going back and forth. One question here, how do LoRa nodes avoid interference among themselves?
Interference among themselves. So on the gateway side, so for the devices that are actually obtaining the transmissions from the LoRa nodes, the gateways have multiple channels. And so the devices can be configured to send to different channels so that on the receiver side there can be less collisions per channel and things like that. And so I'm not sure if it's asking specifically about the receiver side, or like if you have two nodes next to each other, them interfering with each other's transmissions. But at least on the receiver side, the gateway is able to set up multiple channels that you can configure to send data to, and kind of and I believe that there's also some configurations on the gateway that you can that it can recognize when a channel's been used, I think, has received two things at the same time, and handle that accordingly. So
that's helpful. Thanks, Clint. We'll take another question here. Does OTA attachment require an uplink like via cellular or Wi-Fi to exchange keys, or does it happen over LoRaWAN?
So, okay, that's a good question. So basically, it depends on where the key is being transmitted. So the join server will create these session keys, and they have to make it to the node eventually. And so the join server will create these keys and send them over like your standard network, like via Ethernet or Wi-Fi, from the join server to the gateway. And then the gateway itself has a LoRa transmitter on it as well, so it can send and receive. So when it receives the key, it will have to send it via LoRa to the node, because the node itself, there's no requirement for it to be connected to the network. And really, it shouldn't be for the low power specification. It just has the radio itself, the LoRa radio, I should say.
Thanks, Clint. We'll take one more question. Sorry, people keep asking questions, so it pushes me to the bottom here. Are all gateways connected to the internet? Can we not go gateway to gateway with LoRa?
Gateway to gateway. So what I'm describing here is really the network topology of the specification itself. And so the spec doesn't define any communication between the gateways themselves. Their job is really just to be forwarding packets back to their connected network servers. They're really just LoRa receivers and transmitters that demodulate and are really just glorified like packet forwarders as well. So as far as I know, there's no communication between these, but depending on what type of development you're doing, you can monitor, depending on the tools installed on your gateway or how your gateway is designed. If you, I don't know if the question is more specifically, do I have to have the server set up to be able to get my data? Well, in the full topology, yes, but then, practically speaking, no. You can really actually, I'm sorry, let me back up a bit. That's not true. You won't be able to get the data itself unencrypted from the gateway. So the servers really have to be there in the LoRaWAN topology to be able to decrypt the data itself. So short answer is, I don't know of any communication setups between gateways. And in order to decrypt the data, you have to have at least access to the keys to be able to decrypt, which in the topology are stored on the server side of things.
Thanks so much, Clint. Very helpful.
Good. Okay, so this last section is pretty short. I just want to talk about LoRaWAN in practice, and this is kind of the setup that I did at Cardinal Peak, just as a way to kind of jumpstart development. And it's a really cool open source project that's out there that allows you to quickly jumpstart some development with either gateways or nodes themselves, and not really have to worry about the server side if you don't have the infrastructure in place for doing that. And so, to really just quickly start testing, hey, does my node work? Does my gateway work? You can use this open source project to do this. So this is called the Things Network, and the Things Network is a decentralized open source LoRaWAN network that really the goal of it is to make a crowdsourced LoRaWAN network. So this really feeds off of the principle that we talked about earlier, where nodes can send data and it will be received by any gateway that's in the area. And so that backhaul network, if you configure your gateway to be connected to the Things Network servers, then the Things Network provides the server-side implementation for you, so that all you have to do is, if you're in range of a gateway that's been set up by someone and connected to the Things Network, then your end node is then connected to the Things Network, and you can monitor traffic coming in and out from their web console, which is really cool. And you can also set up your own gateway, which is what we did at Cardinal Peak. And so they provide some different tools as well, some SDKs for creating like little applications with the received data to including things like Python libraries and JavaScript. And I put some documentation there that kind of shows the full capability. They also integrate into some other IoT-based web tools as well to kind of import the data. So it's pretty useful for getting things up and running. So this is our gateway on the Things Network. So we set up a gateway at the office, and just to kind of have it in our area, you can kind of see it's the only one. There were a couple more around, but the Things Network website has a map on there, so you can just go on real time and see, hey, are there any gateways within my region? And depending on whether or not you can communicate with those will depend on your environment and how close you are, what obstructions there are from your node, the radio configuration of your node, and things like that. So, but anyway, nevertheless, it gives you the opportunity to see if there's anything available in your area, or add to the network itself, and provide a means for someone else. And kind of in looking through this, I remember in more like urban areas, and especially in Europe, there's a lot of this going on in Europe. I think the Things Network is I believe they're a Dutch company, actually. And so there's a lot more development going on, and they show a lot of examples of tons of gateways set up in Amsterdam and things like that. So it's a cool concept, and for like prototyping, it's really powerful because you don't have to worry about the rest of the network. Okay, so my goal with this is, to give you some information on all of these topics, and hopefully you now have like a basic understanding of everything, and it makes sense. And I just tried to gather a large collection of resources as well that I found really useful in learning about these technologies. So this is just the list here, and there's a couple of more like coursework resources on here. So the LoRaWAN Academy is provided by Semtech. And so those two are closely related, just because the LoRaWAN is like an actual documented specification. So it's used by a lot of people. And so that's more of like a course where there's different modules and videos associated with it. That's very helpful. So I'd highly recommend that to anyone that wants to, review some of this content, but then also kind of get a deeper understanding as well. I put links to a couple of really in detail things regarding like particular aspects of LoRaWAN. So there's a security overview, security in detail. So there's a couple of papers. So one there on security, there's a case study, one on like the physical layer. So if you're like an RF person, that would be a really interesting thing to look into, because it gives the kind of like mathy details of how all this is working. And another really useful one is, the last time I did this presentation, a lot of people were asking, how does this work in practice? Like if we physically take this out, how's it going to perform? And that's a really difficult question to answer, because it really depends on the environment itself, and like obstructions, and if you're in a rural or urban environment. And that case study that's 3 from the bottom is from the University of Singapore, where I think it was like a master's thesis of some students that did like a really detailed analysis of different configurations of the radio in like an urban and rural environment. And it gives their results based on these different parameters and kind of what they were able to do, and comparing it to what the specification says it should do. So that's an interesting one. And then the final one I want to mention is that reverse engineering LoRa. So this is a presentation by I believe it's a security company, where one of the engineers does like this detailed like analysis of going around and trying to intercept packets and analyzing the packets with his own receivers and things, and trying to understand like how this how all the data is really encoded based on the proprietary technologies. That's another really interesting one as well. And so if you want to get started with, with playing with some of this technology with LoRa and LoRaWAN, there's a lot of hardware tools out there. And actually, after putting these links in here a while back, I have gone back and seen that there's a lot more out there now. So some of the dev boards, so this is the node devices specifically, there's a lot of solutions out there from different companies, but ST has an evaluation board that we picked up that worked well, that kind of gives like a lower level feel of what the LoRaWAN stack looks like and how to configure it and things. There's also like a higher level Arduino, which is the Arduino Pro RF, I think. And that's sold by SparkFun. It's a SparkFun board, but it has a LoRa compatible radio on it where you can install libraries to begin playing with this. And in terms of the gateways, the one that we have at Cardinal Peak is the rack gateway, that's more of like a plug and play option. It's a Linux-based like Raspberry Pi shield that just goes onto a Raspberry Pi and provides the LoRa transceiver for just getting things set up quickly onto the network, and provides the software for it as well. But there is a more powerful ST board that kind of gives a lower level experience with developing software for a gateway itself, like from scratch, instead of using something that's pre-made. So for more of like a development production type thing, that's a little more of a reasonable starting point, depending on the hardware you're using. And one cool thing I wanted to point out is that when I made this presentation, there was just like some basic announcements about a LoRa SoC that was being developed. So a lot of these other boards actually are modules that have been created. So it's not a like a single chip solution that has a LoRa radio in it. It's like a module that's developed with like an STM32 as well as a Semtech module for the LoRa radio. And the cool thing about this was ST announced that they had an SoC that was an STM32 with a LoRa radio all in a single chip. And so they hadn't come out with any development boards for this at the time, but I just looked yesterday before the meeting, and it looks like they have released some development boards with this SoC since then. So this would be a really interesting solution because it kind of minimizes the footprint on a particular solution for like a single chip. So that's an interesting thing, and I think that I want to say that they had one that also worked with Bluetooth, like it had a Bluetooth and LoRa compatibility, but I don't remember the details on that exactly. But anyways, those are just some actual like physical resources for development environments that you can purchase and get set up either for working on development within your companies or just for personal interest. So that's all the content I had. So I think we have a little under 10 minutes. If there's any more questions, or if anyone just wants to chat about anything, we can use the rest of the time to do that.
Thanks so much, Clint. We have a lot of questions and just a lot of general interaction on the chat here.
Okay.
So if I missed your question, please feel free to unmute yourself or reach out directly to Clint after the presentation via LinkedIn, or we're happy to connect you. One very popular question, Clint, are you comfortable with sharing your slides after the presentation? If you send those to me, I could share those out broadly.
The slides, I don't see any problem with doing that. There's nothing, all this is just found from, available resources. So I will double check, but I don't foresee any immediate issues with that. And I'll send those to you.
Thanks so much, Clint. And yeah, just as a reminder, this presentation was recorded, so it'll be on the Riot YouTube channel and the meetup page where you registered for this event. We'll move on to questions now. One here. What would be your recommendation for point-to-point encrypted LoRa mesh without a gateway?
Ooh, that's an interesting question. So point-to-point. So at least from my understanding of the question, it would have to be, it would have to be something, proprietary. So obviously that doesn't fall into like the LoRaWAN topology spec. So that would have to be some sort of, custom. That would have to be some sort of custom solution where you'd have to, instead of just having, transmitters at the node level, you'd have to have things that could receive as well and decrypt. Because really, if with the technology itself, you can completely strip down the, say for example, like starting with the full LoRaWAN network, you can strip that down as much as you want if you wanted to, create something custom, where then the nodes itself would have to be able to receive and have to have a receiver side, whereas, so that would consume more power, because they'd have to be able to receive, demodulate, and unencrypt as well, and use the data in a meaningful way. So I guess really the biggest consideration there is, how does that affect your power, and if that's particularly important to you, or if there may be a better solution out there for like communicating in more of a mesh style. I know that there's, different developments for things like Bluetooth mesh and doing things like that, but I don't know that I've specifically heard of like a mesh network type setup for LoRa itself. So sorry, I don't have a better answer for that, but that's just kind of my initial take on it.
Thanks so much, Clint. Another question here. How is the Helium network compatible or competitive with LoRaWAN and the Things network? And then follow up, any Helium network advantage in the US?
Helium network. I'm actually not familiar with that, so I'm not sure I can answer the question.
No worries.
Clint?
I know we have Travis Teague here, so
yeah, if someone can give some background on that. I'm not familiar with it.
So yeah, absolutely. A great presentation. That was very clear.
Thank you.
Explanation of how LoRaWAN works. My name is Travis. I am actually developer growth lead over at Helium Systems, and I posted a link to our network coverage. And any device that is LoRaWAN compliant is absolutely usable on the Helium network. And especially in the US, if you're looking for coverage, like Clint mentioned, it has a very strong foothold overseas, but in the States, TTN just really didn't pick up the momentum. And if you'd like to take a look at Helium, I would absolutely recommend you at least check it out. It's a very, very interesting ecosystem that is LoRaWAN based, but it also has a blockchain element in it, which allows you to earn cryptocurrency, HNT, by providing network coverage and validating network coverage among other gateway operators.
So Caroline, this is Jay from Cardinal Peak, and Clint, I'm sorry we didn't debrief on this before this presentation, but we are actually going to be announcing a partnership with Helium as a company next month as a system integrator. So Jonathan back at the office, Clint, actually has one of their hubs hooked up at his house. We're literally, as we speak, getting used to the Helium interface and have just started to kind of get ramped up on Helium. So we actually do have a announcement coming out, like I said, later this month as a Helium partner.
Very
Great.
cool.
Well, there you go. Nice. Thanks, Jay.
Sure.
So Travis, the cryptocurrency aside, are there other advantages to Helium other than, it's just another LoRaWAN network, right?
I'd like to say it's not just another LoRaWAN network, but in the past little over a year, we have rolled out and actually deployed, not just purchased, but deployed over 17,000 hotspots, not just in the US, but in Canada. We recently opened up into Europe and are going worldwide now. So if you want coverage, just check out the map that I posted into chat here, and you'll see that in most major US cities, we've got some pretty nice coverage, and it's very easy to add on to the system. We are developing it at a very fast pace right now, but we've got a great team over here and are able to get these, get features rolled out in very, very fast order. So just the account on the Helium console is absolutely free. We're rolling out new features, pretty much weekly. And we've got some great things coming up. Grab an account, check it out, and play around with it. Like I say, anything that you use hardware-wise on the Things network or other LoRaWAN networks can absolutely be used over here at Helium. So we also have a great community, very, very active developer community. And we actually, I'm running a call, Helium Hacks Happy Hour. I got to plug this, sorry. This evening, or actually here in 2 hours, if you'd like to drop in and check it out. So.
Thanks, Travis.
Thank
All
you.
right, guys, we're wrapping up here today. If you have any more questions that were not answered, I apologize. I did see some just great dialogue on the chat again, but I just wanted to thank you, Clint, so much for the very educational and helpful presentation. And thank you, Jay Lent, for setting this up. We appreciate you being here, everyone. Take care. Enjoy the rest of your day.
Yeah, thanks for joining, everybody. I really appreciate it.
Thanks, guys.
All
Bye.
right.